Hello everybody. Today we're going to be talking about the ideal gas law. Now this law is going to be very useful. We'll be using this when pressure, volume, temperature, and moles are given. And you will see that later on this can be used in stoichiometry as well. So the ideal gas law is a relationship between these variables, between pressure, volume, temperature, and the number of moles of a gas. If you look at the equation and you break it down, it's PV equals nRT, where P is in pressure, V is volume, N is the symbol for moles, T is temperature, and R is something new called the ideal gas law constant. The value, because it's a constant, is 0.0821 liter atmospheres over mole Kelvin. Now, there are other values for R. We're going to focus on this particular one. So, it is very important when we use the ideal gas law that we match the units of the constant R. As you can see here, the constant R has these 4 units. So, the volume needs to be in liters to match the liters that you find in R. The pressure has to be in ATMs. If they give you something in grams, you got to change it to moles. Okay, you can't use grams. You would have to divide by the molar mass of the substance and change it to moles. And the theme with temperature is that all gas laws, the temperature must be in Kelvin. So usually we'll give you something in Celsius, you got to add 273 and change it to Kelvin. So it is very important that these units are consistent so that they cancel out. So, this is a summary of what I just said. So one of the most important things to remember when plugging in these values is that the units must coincide. Okay, so for example, if you are given a pressure value in ATMs and one that's in millimeters of mercury, they have to match. And because the R value we're using is in ATMs, we have to change whatever the pressure is into ATMs to match that so that the units can cancel out. Now this also applies to the other units as well. So you're going to notice that we already covered pressure conversions before, so that should not be a problem in changing the pressures most likely into ATMs. Also, you'll notice we did temperature conversions, and the one really to focus on is this one here from Celsius to Kelvin. I do have here the conversions from Fahrenheit to Celsius, okay, or Celsius to Fahrenheit, but I would not worry about that. You will not be given problems in Fahrenheit. If anything, they'll be already in Kelvin, or if they're in Celsius, you must change to Kelvin. On the bottom here, I also have some of the conversion factors that are equal to 1 ATM. As you can see, 760 torrs is equal to an ATM, so is 760 millimeters of mercury, 101,325 pascals, and 14.7 psi, or pounds per square inch. On another note, remember that a kilopascal is equal to 1,000 pascals, so we can also use this conversion that an ATM would be equal to 101.325 kilopascals. That would be another valid one to use. Now, here is how to isolate these variables. Okay? So, if you are looking for pressure, and here's the original equation to isolate algebraically P for pressure, you will be using this first equation. If you're looking for volume, do the same algebra. You would use this second equation. If you're looking for moles and you isolate N, you'll be using this third one. You won't really be using this one because we won't be finding R. R is a constant, so that value will always be 0.0821 in liter atmospheres over mole Kelvin. You might be asked to solve for temperature, and then therefore that would be the formula there. So these are all the different possibilities that you may be asked to find. Now, one other note that we need to remember is you were told what STP is earlier. STP is an acronym for standard temperature and pressure. So if they tell you that it is at standard temperature, then automatically you're going to plug 273 Kelvin as the value. If they tell you it's at standard pressure, you're going to plug in 1 atm. If it says STP, then obviously that means those two numbers are the ones you're going to plug into the formula if it's under STP conditions. Okay? So for now, those are the only ones you really need to worry about. All right. So let's do a simple problem here where this one's not going to require many conversions. We'll start easy and then we'll gradually build up here. So if you look here, it says calculate the volume. So we're looking for V. They're giving us a few important givens here. The moles is 0.845 moles, okay, of nitrogen gas. And they give you that the pressure is 1.37 atms and that the temperature is 315 Kelvin. Now, R is a constant, so you'll have that on your formula sheet, okay, or you might be asked to memorize it, and that's 0.0821 liter atmospheres over mole Kelvin. So, the original equation is PV is equal to nRT, so what we're going to do is we're going to isolate the volume. We're looking for volume here. So, if you isolate volume, it's going to look like this. nRT divided by P will give us the volume. Now, before we plug in numbers, let's do a quick check. Is the moles already in moles? Well, the answer is yes. Is the pressure in ATMs? Yes. Is the temperature in Kelvin? Yes. So we answered yes to all those questions. So we're ready to put the numbers and substitute it into the equation. So let's solve for V here. The moles is 0.845. There's your first number. We're going to multiply that by R, which is 0.0821. Let me squeeze in the units here. Liter, atmosphere, mole, Kelvin. Has 4 units. And then you got your temperature at 315 Kelvin. That's going to be divided by 1.37, which is the ATMs, the pressure. And that will give us volume. Now, when you do the math, watch what happens. This is the importance of having the units cancel. You'll notice that the moles will cancel. You'll notice that the ATMs will cancel. Okay, so the Kelvin, the only unit left is liter, which is what we want. We're looking for moles. I'm sorry, for volume, which is expressed in liters. So when you do the math here, you're going to get 15.95. And if you look at significant digits, the smallest number in all the givens is 3 significant digits. So let's round that to 3 significant digits, and that comes out to 16.0 liters. And that will be our answer to this first problem, okay? All right, let's take a look at another problem here. This one, we're going to start adding some conversions. So this one's going to get a little bit more complicated. So they're asking us to find the number of moles of a gas. So let's put here a question mark. And they tell you that the pressure is 24.2 psi, which is pounds per square inch. They give you the volume of 3.2 liters. They give you a temperature of 25 degrees Celsius, and then our R value is still going to be 0.0821 liter atmospheres over mole Kelvin. Now, this time we're looking for moles. So again, PV is equal to nRT. And we're looking for N this time. So our working equation is going to be P times V over RT gives you moles. Now, before we start, we got to make sure our units are correct. And if you notice, our pressure needs to be in ATMs, and it's not. So what we're going to do is let's convert it to ATMs. In 1 ATM, if you recall, there are 14.7 psi, so that units cancel. And when you multiply by 14.7, you're going to get a new pressure in ATMs of 1.646, and that'll be ATMs. Now that checks out, okay? Let me erase this here for a minute. Okay, there we go. And then the temperature has to be in Kelvin, so we're going to go ahead and add 273, and that'll bring us to 298 Kelvin. And if you look, now this is in ATMs, this is in liters, this is in Kelvin, and this is just your constant. So everything is now good to go into the equation. So we're solving for moles this time. So to find moles, what we're going to do is we're going to put pressure on the numerator, which would be 1.6. Let me make that a little clearer. 1.646 ATMs times 3.2 liters. That'll be your top. We'll multiply those in a second. The bottom will be 0.0821, and the units, that one has a lot of units, so let's write them in here, get you used to canceling out units. Liter atmosphere over mole Kelvin, and then your temperature is 298 Kelvin. Now, again, watch how the units cancel. So if you notice, your ATM here will cancel with the ATM, so will the liters. Okay, so will the kelvins. The only thing left is moles. Now, when you put this into the calculator, you'll see that you get, the top is 5.2672. The bottom, I actually worked this out for you, is 24.4658. And then when you divide those numbers into each other, you end up getting 0.215. Now, we're going to round this because notice that 3.2 has only two significant digits. So we're going to round this so that the answer is 0.22. We're going to bump that up here. Moles. And this will be our answer to the number of moles of gas that would be needed to inflate the basketball. Okay? Let's take a look at one more. And if you look here, this time they want the pressure, but look at this, pay attention to this. They're being picky. They want the pressure in millimeters of mercury. So we might have to do an extra step there, and that shouldn't be a problem. Now, notice they didn't give us moles. Instead, they gave us grams. Well, look what I'm going to do here. Let's put here moles, because I can use grams, and I can convert that to moles. I'm going to write down the given, and in a moment, I'll show you how I can change that to moles, because it is 0.133 grams of helium. Okay? The temperature is fine here at 32 degrees Celsius, and the volume is 648 milliliters, and then we'll write R down over here. Okay? All right, now this time we're looking for pressure. So if you look at the equation that we've been using, PV is equal to nRT. We're looking for the P this time. So our working equation will be that the pressure is equal to nRT over the volume. Now, we got to do a couple of adjustments. We need to change grams to moles. If you recall the molar mass of helium, okay, from the periodic table, helium is 4.0 grams per mole. So if we divide 0.133 grams by 4 grams per mole, write that over here, by dividing, we're going to change this, okay, into moles, and the number that I get here, I'll write it down for you, is 0.03325 moles of helium. We got to also change the temperature. So we got to add 273 to 32, and that gives you 305 Kelvin. And then here's something new. we need to change milliliters to liters. We can't use milliliters. Now, if you recall, in 1 liter, there are 1,000 milliliters. So to convert from milliliters to liters, all you got to do is divide by 1,000, and you're going to get 0.648 liters. Okay? At this point, we have our moles are now in the proper units. Okay? This temperature here, this is a 305 here. So this is in Kelvin, this is in liters, and R is over here. Okay? So let's take a look here and let's go ahead and solve for pressure. So in order to find pressure, what we're going to do is we're going to get that, let me write a little line here. P is going to be the moles. So let's put here 0.03325. Okay, now that's moles. And we're going to multiply that by R, which is 0.0821, and that's liter atmosphere over mole Kelvin. Okay, I'm putting the units on the bottom so it'll fit in the screen. And then you got your temperature, which is 305, and that's Kelvin. Now, that will be nRT, and on the bottom, we got 0.648 liters. And again, I'm going to illustrate how when you do the cancellations here, okay, you're going to see that the moles cancel, so do the liters, and so do the Kelvin. Okay? Now, when you do the math and you multiply the top and divide by 0.648, we're going to get a pressure equal to let me give myself a little room here, 1.28, but notice the unit. The pressure comes out in ATMs, and that's normal. That's what it should come out in. So this is 1.28 ATMs. But if you read the question, they don't want the answer in ATMs. They want it in millimeters of mercury. Be very careful when you read these questions so that you answer what they want. So we got to do one extra step. Not a big deal. Let's convert ATMs into millimeters of mercury. You see, in 1 ATM, and I'm putting it on the denominator so they can cancel, there are 760 millimeters of mercury. By setting it up this way, the ATMs will cancel, and you're going to multiply here, and we're going to round this answer. I get 976.5. Let's round that to 3 significant digits, okay? And that will be 977 millimeters of mercury. Now, the reason we round it to 3 is because when you change this to Kelvin, it's 305, and that one has 3. So 3 is the lowest. Okay, so our final answer in millimeters of mercury would be 977. Okay? Now, let me give you some final thoughts here. So it is very important that if you're looking for moles, you saw what we did in one of the problems. If it's in grams, you have to divide, okay, by the molar mass to change it to moles. Now, what you need to be careful with is make sure you remember the correct molar mass, because some gases are diatomic. For instance, hydrogen, the molar mass is going to be 2.02, okay, grams per mole. All of these are going to be grams per mole. So if you forgot that hydrogen was diatomic, you would only use 1.01. Another popular one would be nitrogen. Nitrogen is 14.01, but times 2, because it's diatomic, it's 28.02 grams per mole. Oxygen, okay, is 16, but times 2 would be 32 grams per mole. Chlorine is another one. It's 35.45 times 2, which is 70 let me see what that is, 35.45 times 2 is 70.9 grams per mole. And fluorine is another one. That one is 19 times 2, which is 38 grams per mole. Now, other substances that are diatomic are iodine and bromine, but usually iodine is a solid at room temperature and bromine is a liquid at room temperature. Unless they say it's a gas, then you make them diatomic. If not, the ones you should worry about are the first 5 here, because those are gases all at room temperature. One other thing I wanted to mention is don't forget with volume that a milliliter is equal to a cubic centimeter. So if you see that the problem says cubic centimeters, that's really a milliliter. And that's no good. You need to change volume to liters, which, by the way, a liter is equal to a cubic decimeter. So if the problem has something already in cubic decimeters, it's safe to say that it's already in liters. You're good. You don't have to do anything. But as you saw in one of the problems, if you are given something in milliliters or cubic centimeters, you must change to liters. And in order to do that, when you saw me set this up, you're going to have to go from milliliters to liters, you got to divide by 1,000. Okay? And when you divide by 1,000, that'll get you to liters, which happens to be the same as cubic decimeters. So that's something important that you should remember. And then, of course, I don't need to mention too much about temperature. We all know if it's in Celsius, add 273 and convert it to Kelvin. And as far as pressure, remember all those conversion factors that we learned before. Because the goal here is when you use the ideal gas law, the units have to match the units of R. And since we're using 0.0821, the volume has to be in liters, the pressure in ATMs, moles has to be in moles, not grams, and of course temperature has to be in Kelvin. And if you do that, then you will be fine. Okay? So I believe those are all the pointers that I needed to stress. But do keep in mind, don't forget those gases that are diatomic, which are on this page, okay? Because if you forget they're diatomic and you need to change them to moles, you might be using the wrong molar mass. All right? Thank you.